Unit 11 is all about energy of reactions. How is energy consumed? How is energy released? How is the change of energy? Everything you want to know about energy and probably a whole lot more. So first, as we begin Unit 11, let's talk about the vocabulary. So there's something called a system and the surroundings. This is just a general term. We could kind of use them in generic contexts, but we need to understand what they mean. So a system is basically where the reaction occurs. Now, in chemistry, that could often be a beaker, that could be a flask, that could be some sort of glassware where the reaction occurs. In biology, that could be our cells or an organ. If we're talking about, say, weather patterns, that could be the clouds or some sort of warm front or cold front. It's basically where the reaction is happening. Now, the surroundings, as you might guess, is everything outside the system. Literally everything outside the system. Oh, I forgot the word outside. Everything, the system. That makes a lot of sense. Outside the system. All right, so for example, if we're cooking on our stove back in our kitchen, then we may have like a pot of water. We're boiling the pot of water. The system would be the pot and the water that is boiling, right? The surroundings would be the stove, would be the air around the stove that we're heating up. We're starting to get a little bit hot because we're in the kitchen. I am the surroundings, the counter is the surroundings. Everything else is the surroundings, right? If we're doing a reaction inside of a beaker, the reaction is the system. The table that the beaker is on is the surroundings, the air that is around the beaker. Again, everything outside the system is called the surroundings. Now, what we're going to talk about in this unit is how does energy move into or out of the system? And as energy moves into the system, it has to come from somewhere, and you guessed it, it came from the surroundings. Why that is the case is because the first law of thermodynamics, basically, which says that, let me make sure I phrase this correctly, that energy is finite, that heat is a form of energy. Let me phrase this correctly. Heat, my H's are just not working well. Heat is a form of energy. Therefore, heat is conserved. You guys all know basically the first law of thermodynamics, which says energy cannot be created nor destroyed, right? That's an R and that's a V. Sorry, guys, my pen is not cooperating today. That heat is a form of energy. Therefore, if the first law of thermodynamics says that energy cannot be created nor destroyed, guess what? Neither can thermal energy or heat. So that's what that says. So like I said, if it is coming from somewhere, it has to be going somewhere and vice versa. We don't just create it. We have to move it or make it flow or make it change, but it doesn't just come out of nowhere. So what is heat exactly? Heat is the flow of thermal energy. Heat is technically the flow of thermal energy. So that's kind of weird because, again, remember, when we're talking on a day-to-day basis with just average people, we might say the word heat, but by definition, heat is the movement of thermal energy. For example, if I have these two blocks at the bottom of your screen, it says that A is of higher temperature than block B. When I put them together and they're in contact, the heat will flow always from the hotter to the colder object. It never goes the other direction. It will always go from what is hot to what is colder. Therefore, they will equilibrate. And the very last image on the right, the purple, they have now reached a similar temperature and the flow of heat stops. So if A is not in contact and cannot come or influence B, then we cannot say there is any heat. They have different thermal energies, but if they do not flow, then there is no heat. Whereas in the middle image, there is a heat flow, so there's definitely heat. And then in the very end, they are now equilibrated, so there is no flow of heat. It's kind of a weird thing to say, but it works. That's the way it works. Something that the thermal energy has to be moving for there to be, by definition, heat. All right, that being said, let's talk about, again, what exactly is temperature? Because again, another thing we talk a lot about, but maybe not in the textbook way, but temperature, which we often use interchangeably with heat, is the average kinetic average kinetic energy of the molecules. So when we use a thermometer, what we are actually measuring, we always say temperature, right? Well, we're really measuring the speed at which the molecules are vibrating and traveling. The faster they're traveling, the higher the mercury will go on our thermometer, and it will show that it's a higher temperature. Temperature is kind of a way to measure literally how fast the molecules are moving. And again, heat is actually the movement of thermal energy from one object to another object. And remember, it only goes from what is hot to what is cold. It never goes the other direction, okay? All right, so we need to talk a little bit about something called endothermic reaction and an exothermic reaction. Like the prefixes kind of suggest, endothermic means that the energy is going into the system, as you see in the pink box. The energy is going into the system. Where it comes from, of course, is the surroundings. What we're going to say is that the delta H, which is what we're going to call enthalpy, or the change in heat energy, is going to be greater than 1. The system is going to gain energy. Therefore, it's going to be a positive value as it increases in thermal energy. Excuse me. On the right side, we have the opposite. It's called an exothermic reaction. An exothermic reaction, as the prefix suggests, the energy, the energy will be leaving the system and therefore going into the surroundings. Remember, it has to go somewhere. So therefore, the system, the blue box, is losing the energy. Therefore, its delta H, or enthalpy, change in heat, will actually be decreasing. Therefore, its value would be negative. It's losing energy, therefore it is negative. On the endothermic, it is gaining, therefore it is positive, okay? Make sure you guys know that, first of all. Second of all, like I said before, the way that heat flows, it must go from hot to cold. And the first law of thermodynamics also says that energy, or in this context, heat, cannot be created nor destroyed. So I want to talk really quickly about refrigerators. Refrigerators are kind of interesting, right? If you ever wondered how they make things cold, we can't really create cold. Cold is basically, and now don't go down that rabbit hole because you might find conflicting definitions, but cold is basically the absence of heat. On a hot day, we have a lot of heat, a lot of thermal energy, and on a cold day, we have the absence of that heat, okay? So cold is literally the absence of that heat, of absence of thermal energy. So in order to cool your refrigerator, have you ever noticed the back of the refrigerator gets very hot? Or even the outside, the front sides, all of it gets very hot, but especially in the back. The only way that we could cool the contents inside the refrigerator is to remove the heat. So we take the heat out of the inside of the refrigerator using the compressor and the machinery of the refrigerator, and it has to go somewhere. So we put it outside the back using those coils you may have seen that dissipate the heat. So we are literally extracting the heat from the inside of the refrigerator. It has to go somewhere, so it goes into the surroundings, which we call our kitchen. By removing the heat, what we are effectively doing is making the refrigerator inside colder. So that's just a context of these particular exo and endothermic. So that obviously would be an exothermic reaction. We are taking the heat from the system, which is the inside of the refrigerator, and we are releasing it to the surroundings, which again is the kitchen, thereby making the inside colder, or more correctly, less warm. All right, that being said, again, we just talked about delta H a little bit, so I'm just going to finish up real quick with that. Delta H, again, is the difference between the heat of the products versus heat of the, you guessed it, the reactants. So it's a comparison of where we're finishing versus where we are starting. Yes, I'm doing that backwards on purpose. The products is what we want to look at first, and then we subtract the reactants. So the way we would do this mathematically is it would be the change in heat of the products. Again, this sounds really similar. I'm just doing it more in a mathematical sense, minus the change in heat of the reactants. Now, to really show it in a math, what we do is delta H As you guys may know, this is the capital D symbol in the Greek language. We use this to mean change. And then you guys may have seen this before in a previous unit. That is also the letter D, but the lowercase. And we use this to show partial. So just so you guys know, again, that's where we get these letters from. That's the capital D. This is the lowercase d in the Greek alphabet. The triangle, delta, means change in heat. So it'd be the delta H of the products, that's subscripted, minus the change in heat, or delta H, of the reactants. That's the actual mathematical representation of delta H. Okay, all right, guys, that's a good foundation for energy, heat, and temperature, all things that you will need to understand going forward in Unit 11.